Dear all, welcome to the lecture on boundary layer flow, part 2, lecture 1 on aerodynamic forces. In this lecture, we will be discussing about external internal flow, static and dynamic and total pressure, then Bernoulli's principle, I revisit a measurement of static and stagnation pressure, skin friction and pressure drag. First, we'll look into what is internal flow. When the flow is internal in nature and subjected to confined boundaries, and we call those are internal flow. For example, flow through a AC vent, blood flow in a vessel, blood vessel, and flow through pipes are internal in nature. And then what is external flow, where the whole structure is covered by the fluid. For instance, the flow is external in terms of trucks. You can see the streamline pattern, and in terms of setback building, you can see any buildings will be the flow is external in nature, and wind turbines where the wind drives the turbines to rotate. The flow happens over the blade, the force is being exerted on the blade, and the rotation is due to the lift component of the force. So obviously, and these are some examples of an external flow applications. And we say that what is static, dynamic, and total pressure. Here you can see that if the flow is going to happen this way, and we can keep a object over here, and what will happen because of this, the flow, you can see that body moves along with the flow, the pressure exerted by the fluid, okay, but there is no dynamic effect. This is a static effect. It's nothing. We can also say that it's a hydrostatic pressure. The static pressure is exerted even on the walls and all through the surface. We call that as a static pressure. So we can measure the static pressure using a piezometer, and you can obviously calculate what is the pressure head. And we can say that it represents the actual thermodynamic pressure of the fluid, and this is same as the used in pressure in thermodynamics and other property tables. Then we look into what is dynamic and total pressure or stagnation pressure. We consider a flow happening over here, and then we have a obstacle over here. What would happen due to this obstacle? The flow would get separated, and the flow gets separated like this because of the obstacle. You can even feel that when the flowing water is going, and you can put your hands over a flowing water through a channel, you can find part of the separation happening around the surface. So what would happen because of that? The separated flow would happen. But I want to know what is the pressure, because when the flow is coming at this part, what will happen? The total energy would be there. The total energy is nothing but the sum of static and the dynamic pressure would be there. At this point, or we can say the potential and kinetic energy, in other words. So when the velocity at this point will drop down to zero, so the kinetic energy is being converted into the potential energy. So to identify that, we can introduce this is the flow getting separated, and we shall introduce a pitot tube. By introducing a pitot tube over here, and the flow gets into here, and you can able to measure the stagnation pressure. Okay, and we also see that piezometer helps us into determining the static pressure. So we can say that total pressure is nothing but, or the stagnation pressure is nothing but, I am representing stagnation pressure as S, and static pressure is P, and then dynamic pressure is T. So we shall able to calculate what is the dynamic pressure. So that is going to give us a dynamic pressure, which is the difference between the stagnation and static pressure. Obviously, we cannot find the dynamic pressure directly. So this way we can calculate what is the dynamic pressure. So stagnation pressure is nothing but sum of static and dynamic pressure. And we'll just give a revisit to Bernoulli's equation. And again, we consider the same example where the vertical flat plate is obstructing the flow. We say we call this a streamline pattern. When the flow comes here, these are individual streamlines. You consider only 3 streamlines, and the flow getting separated from the and then this is at this point we are going to study how do you measure the we shall measure the piezometer, the static pressure, Pitot tube for the stagnation pressure, and we shall apply the Bernoulli's equation to this any of the streamline, And we shall see that the kinetic energy of the particle, we shall coming over here. I say that the flow comes over here. What is the total energy in this streamline? If I consider small particle, would be half mv square, where m is the mass of the molecule, v is the velocity of that particular molecule. So if the packet of fluid is coming, we can consider a hole, and if the flow is coming and hitting over here, so on that object, so total pressure that is being imposed, what is the mass, is going to be the density over here. So half rho v square is the dynamic pressure that is imposed on the object. So which I can able to calculate from the difference of stagnation and the static pressure. So here you can apply the Bernoulli's equation for this streamline. Let's see applying a streamline. We consider this streamline. In this streamline, if you apply the Bernoulli's equation, at this location we can say the pressure is could be P plus half rho v square, and it comes over here. What will happen? In this case, the velocity would be the total pressure. It will be the stagnation pressure. The stagnation pressure will be P plus half rho v square. At this point where fluid is being stopped and the velocity is dropped and the kinetic energy at this impact is zero. So we can say that the static and stagnation pressure are specified at the location. By this Pitot tube, we shall also calculate what is the velocity. The fluid velocity can be calculated with this way. P stagnation minus P will be the static pressure, will be equal to half rho v square, which is nothing but a dynamic pressure. And we shall also calculate what is the V from rephrasing this equation. 2 into P stagnation minus P static upon rho the square. Then we have one more instrument for measuring the Pitot-Static, static and stagnation pressure together. We call that as a Pitot-Static Probe. We use a piezometer, earlier case, but we are going to avoid using the piezometer, which means if, for example, if we have a pressure that is less than the ambient pressure, the atmospheric pressure, we say that we'll have a vacuum pressure, and in that case we cannot use a piezometer. Okay, so we have to think about a new device instead of going with that. So we shall introduce small ports along the surfaces, okay, around the circumference of the pitot tube. So we shall also connect those to the manometer in the sideways, so we can able to get what is the static pressure and stagnation pressure together in a same device. So we say that it's an example that is shown here, where you have a stagnation pressure measurement from the big hole, and there are sidewise, there are about 5 holes in the circumference. 2 are shown here. Those are going to give us a static pressure holes. Pitot-Static Probe is convenient to integrate static pressure holes because we are measuring the stagnation pressure, at the same nearby you are measuring the static pressure. And Bernoulli's, there are some limitations with the Bernoulli's equation, basic Bernoulli's equation. Those are when there is a sudden expansion, the flow getting expanded. In this case, we cannot incorporate into this Bernoulli's equation. We have to add some parameters, and in terms of long and narrow tubes, and flow through a valve, and when there's wake in these conditions, heating section, we have to there are some limitations with the Bernoulli's fundamental Bernoulli's equation. And again we'll discuss about drag force. We consider a similar flow over a vertical plate, and we can see the streamline coming onto the vertical plate, and we can see the dynamic pressure imposed is we have half rho v square, and obviously the forces, the pressure will be acting on the object, and the resultant can be nothing but summation of these 3 pressures, and we call the dynamic force can be given by half rho v square into this area. We say that earlier, and this is the projected area. If it is a 2-dimensional 3-dimensional case, the projected area would be if I call this is the breadth, and this I will call as the height. So the pressure acting on this one would be the dynamic force. This is the dynamic pressure multiplied by the area. So where the area is the projected area with respect to the flow. If I'm going to draw with respect to the flow, this is the projected area, of this particular three-dimensional object, and the flow is normal to the normal to the screen, and the pressure is acting on this. So I will call B. Sorry, this is the height. So this is the breadth B. So the area of this would be H times B, and we shall say that drag force from a norm will be equal to this, and we introduce a small component which is called as a drag coefficient, which is given by a parameter CD. This is to think about the CD is a coefficient that corresponds to the shape of this object. Okay, and this is a factor that could multiply the whole force so that the size, the shape factor will be incorporated. For instance, drag coefficient purely depends on the shape and can only obtain it by means of experiments or by means of a computational analysis. Okay. So we'll see how the CD is influenced. Let's consider this is going to be a sharp-edged surface, vertical plate. And in terms, if you have a round-edged, okay, if I replace the sound, sharp edge with a round edge, I can able to see the sharp edges and round edges. So the CD for both the cases will be different because the earlier flow getting separated over here, and due to which you will get a different CD, and the flow moves smoothly around the surfaces, you will get a different CD, which means that the flow separation will increase more drag force, whereas the streamlining of this surface will reduce the drag force, which means then the CD of these two would be totally different. So that this we say that this can be obtained experimentally, and it's purely a shape function. So we'll look into how the drag force now. We'll look into the lift force now. So flow the streamline is coming here towards the object. We shall say that this is inclined at an angle. Previously we saw it's vertical. The angle between the wind and the angle between the wind and the flat plate is 90 degree. In this case, it's about 45 degree. I can say that this is the flow in motion and this is the angle. So we call this angle as said to be about 45 degrees. Okay, or we say that this is theta. Okay, and what would happen when the flow is coming? You can see that a lot of streamline, flow is being captured by the object, and the flow getting separated from here. You can see the flow separation, and you can get this subjected to area of we say that high pressure region, because a lot of forces acting on this surface, which means that kinetic energy is being converted the velocity drops down to zero, but more pressure energy is acting here. But at the same time, the flow getting separated here, what happens here is a low pressure region, because the wake is there, the turbulent wake is there. So flow getting separated, and we say the high pressure and low pressure region. So what would be the net resultant force will act in this direction? We shall resolve that resultant force in two directions. One is along the velocity across the flow. Along the flow, we say that drag, across the flow is we call it as lift. So these are the two forces. If you see that in this case, it inclined to 45 degree, so there will be substantial lift as well as drag. And this is the same example if you are traveling in a bike and you can put your hands outside and you can feel that when you put your hands in vertical 90-degree position against the wind, you find more drag. When you slowly come down, you find a lot of lift, and when you place it almost zero, you don't find much lift, but a small amount of lift and small amount of drag. The lift is if you didn't place it properly, maybe there will be a slight flow separating. Both the sides of the hands are not same surface, it's different, and you'll find the drag that is due to the frontal area, but also the friction along the surface of your hand. So along the force we call it as drag force, across we call it as lift force, and we can say along x direction or along y direction. Along x direction, this is drag force. Along y direction is lift force. We shall also look into more clear picture of what are the components that gives rise to the drag force, which are nothing but pressure and viscous forces. We have already seen the pressure forces, so due to the frontal area, and one more is the viscous forces that is happening around the surface, which we shall say the flow is going over the surface like this, that can be exaggerated. And here you can see we have just concept focused on one particular d elemental small elemental length dA. In this dA we have a we'll see what are the pressure forces still acting on the model. So P times dA is the pressure force, and N is a normal normal to the force, so we have N, and we have a shear stress, wall shear, that is going to be given by tau W. And we can able to get what is the DFT. We shall say that the component of drag only in this particular small element dA can be given by P times dA into cos theta, which is along this x direction, along the x direction. And I can also get this along the x direction, which is tau W into dA into sine theta. Similarly, I can compute for lift force, which is dFn along the vertical direction, along this vertical direction, so which is nothing but PdA into sine theta. Okay, and since the force component is coming towards it, so you have negative sign and you have tau W into dA cos theta. So integrating over the whole area, you can get what is the total drag force and what is the total lift force. So lift and drag forces, we can measure the lift and drag forces by means of connecting it to a load cell or a strain gauge. So by this, what you will get is what is the drag force. If you connect a strain gauge, in this sense, in the so the strain appears to be on this, and you will get what is the force in this direction. And if I connect a strain gauge in the horizontal position, so I can able to get the other direction, so I can get what is the lift force. So this is the drag lift force, and this is the drag force. Sorry. By this way, you can calculate what is the vertical force. This way, you can calculate what is the horizontal force. Once knowing what is that force, let's say, from which we can calculate what is the drag coefficient. We have seen that drag force is given by Ft into CD half rho V square into A, and we can also find out that drag coefficient would be CD Ft upon half rho V square. Fd is the drag force, half rho V square is the dynamic pressure into the area. So by this way, you can calculate what is the drag coefficient. Similarly, we can calculate what is the lift coefficient, where CL is given by Fl is the lift force upon half rho V square into A, where rho is the density, V is the velocity, velocity in oncoming velocity, A is the projected frontal area, which is in this case the frontal area. If I project this, how the wind looks like, the flow is coming, the flow when I see from here, so you can see that the frontal area is something like a line in case of two dimensional, and it's going to be a length of this length. The projected area is this this height, sorry, not this height. This is going to be a projected area in this case. But we shall also have in terms of two dimensional. So you have a plate, and you have the third dimension, I call this is the breadth, and this is going to be your height. So total the area can be h times b. So the detailed distribution of pressure, for example, what is the contribution from the pressure, what is the contribution from the shear force, are difficult to obtain by measurements, and it's not mostly required in most cases. This CD will incorporate both drag due to pressure as well as the shear forces. So overall forces acting in aircraft or automobile, we can see the basically if it is in a steady state flight condition, you have these thrust, drag, lift, and weight. So thrust, if you increase the thrust, drag will also increase. Okay. That the thing is, you have to reduce the drag. Once you reduce the drag, you give more less thrust, that will be sufficient, so that you can save a lot of fuel. And also lift is very mandatory in terms of aircraft. So you give change the wings will help us in providing more lift. Okay. And the lift is, should be more than the weight, and drag should be, thrust should be more than the drag. So if this is same, lift is equal to the weight and thrust is, we call this as a steady flight condition. Lift has to, when you want to lift the aircraft, obviously you should get more lift force than the weight force, and more thrust force, sorry, more thrust force than the drag force. And resistance of a on a car, when a car is moving, there is inertial resistance due to the weight of the vehicle, and the wind drag will increase. If you go forward, as the thrust increases, drag will increase. So in all these cases, we look for reducing the drag forces. So effect of viscosity, we'll discuss the what is viscous boundary layer. This is a simple demonstration where this is going to consider, you have a flow around it, whereas you have a higher thick, viscous fluid which has 100 megapascals again, and here you have one more low viscosity fluid, and you can see the boundary layer profile. You can which is highly influenced over here, but in this case the influence is very very low. The distance between, you can compute it. So which says that in this case, lower viscous fluid have a different boundary layer than the high viscous fluids. So components of drag in on with respect to various sections. If you keep a plate, in a horizontal condition, the plate is horizontal in nature. So we say that this is the horizontal plate. So in this case, the boundary layer is something like this. The developed bound, the flow getting, over here, and the boundary layer keeps moving on. The developed boundary layer looks like this. So there is a lot of shear, because this velocity is different and this velocity is different. Due to this, the shear, and between these two surfaces, the fluid and this, there is a, frictional, and that is called as a frictional drag, because the surface and of the solid and the liquid in contact will introduce a lot of friction, and that will compose to, introduced by tau w. As it increases, you can see the effect of tau w. uh, and we can also say that if the plate is kept vertical, you find less, area in contact with the flow. So flow getting separated here and go, this is the wake region. This is a low pressure region indicated in negative signs, which is we call the suction pressure as well. It is going to be a positive pressure or high pressure in this. The flow will tend to go like this and you tend to go like this, and most of the pressure is being, this point is a stagnation point. Okay. And here is wall shear. And what it comes to say here is there is a lot of pressure drag, because the frontal area is larger. So net force would be high pressure minus low pressure. The total force, maximum force would be along this direction, along the drag. Okay. But less due to the friction. If we consider what is the drag along this one, we can see that more frictional drag. In this case, less frictional drag. Here is more frictional drag, but in this case, more pressure drag. We also call it as a form drag or the pressure drag. In this case, more pressure. In this case, more friction. The one important problem with making the object streamlined is the friction drag. So we say the total drag force is summation of friction and pressure drag, and the coefficient should be coefficient of friction and coefficient of drag due to friction and drag due to pressure. And this is an example of how a flow, fluid flow on a flat plate. You can see this surface is subjected to a lot of frictional drag on this side and again on the bottom side. So the coefficient of drag that you get is due to some of the pressure drag. The pressure drag you can calculate, which is nothing but the frontal area pressure, or you can even say that I'm just first finding the frictional, drag force, which is nothing but half rho v square into A This will give you the drag. Okay, it's a frontal, and we can also add with the frictional drag, which is half, where here you have to multiply with CD, and here we will be multiplying with CF. This is a coefficient of friction. So you can see the frictional and pressure drag. And again here you have a high pressure, and here you have, we have seen recently the high pressure region and then the low pressure. So then there will be more drag, the flow getting separated from here. These objects will have more drag coefficient, which is CD will be about 1.222. This is for a circular cylinder. You can see that weight behind it, and a lot of high pressure on the over here. The flow turned to be streamlined, so you'll get a little bit of high pressure in this region and low pressure in this region. Net resultant pressure would give you the drag force. So thank you very much, and I wish to thank all my scholars in our laboratory who helped us in making the experiments.